presentation. It will be a joint presentation together with Cheryl, Chongwang, and Pierre. So you can ask questions to any of us, and we'll try to manage, distribute the answer between us. Get me started with an observation from nature. If we look at the animal kingdom, we observe that all forms of intelligence have an embodiment. And this holds true for very small species like rodents, birds, to higher mammalians like primates, or even fishes. And this becomes in particular relevant when you look at humans. So this is a human kid that is able to juggle while solving a Rubik's Cube. This really speaks to the dexterity and agility that this person has in coordinating movements while really solving a complex task. And he's able to do that because of the complexity of the apparatus of the embodiment that he had at his disposal. Now, not everybody is able to do this task, but everybody is equipped with the same embodiment to be able to achieve such dexterity and complexity of movements. Now, this is something that seems trivial for many of us, especially for the one of us that comes from neuroscience background, but actually is not that trivial for AI. So we see this over and over, that AI in the strides to try to advance the understanding and knowledge really has limitation in understanding what humans' embodiment is. And this is one of the major reasons why they hallucinate. They create results that are outside humans, human reality, human world, because they don't have that understanding of humans that allows that to embed that in the human world, in the human physical world. So this might be an important lesson for artificial intelligence, that if you want to have a human level artificial intelligence, we have to provide with the same human apparatus, that is the human embodiment that humans have. And this is very, very important. The embodiment that humans have is very important because actually our intelligence is constrained by that. And nobody puts that better than Daniel Wolpert, a professor at Columbia University. In a TED talk, he states that humans have a brain for one reason only: to produce adapted complex movements. He's very strong on this. He said there is no other reason to have a brain. And the intelligence that we have is really to serve our motor system. And this is something very important in the way that we are built. So our central nervous system, that is the collection of the brain that's spinal cord, is where our intentions, goal, understanding of the world is integrated. But we can externalize this understanding only through muscle. That is the first layer of the peripheral nervous system. And the activation of the muscle, we move in the world. We interact with the world. We sense the world, and this information goes back to our central nervous system in order to reason through the world that surrounds us. So this loop is the essence of intelligence and motor intelligence for humans and for all animals. But we miss that in most of our reasoning through artificial means. Was that a question or? Okay, yeah. Good. So let's assume that we want to use now our human embodiment in order to understand intelligence. How do we do that? Well, the first thing is that this is not something trivial to consider human embodiment, because the human peripheral nervous system, human apparatus, is very unique and is different from what we typically consider in abstract terms through toy models or even in robotics. Because our motor system, peripheral motor system, is an overactuated motor system. We have way more muscle than degrees of freedom. So it's over-redundant, overactuated. We have a multi-articular system. So multiple muscles are responsible for the movement of a single joint. Imagine your wrist. There are more than 20 muscles that have all an effect on the rotation of your wrist. We have also multi-joints. So a single muscle is responsible for movements of multiple joints. For example, the muscle that is responsible for the bending of the tip of your index finger is a muscle that starts from the elbow and routes through all the joints that are part of that chain that arrives to the bending of your index finger. And also, most importantly, muscle cannot be pulled. So in order to maintain and stabilize your body, you have to continuously control, either by activating or suppressing activation of muscle to coordinate your body. So it's not a process that you just position a muscle in a point and then you observe the movement. You have to continuously control the whole body. And that's a really important, unique feature of the control mechanism, is the continuous full system control, rather than a sparse system like we might have in robotics or other type of actuations. So given this complexity, our North Star is really that we want to understand the human level dexterity and agility. And to do that, we need to create physiological twins that are able to replicate as accurately as possible humans' embodiment. And this is because if we are able to unlock that, that's the first step to tackle human intelligence, starting with the motor behavior and motor intelligence. And this presentation today has covered these two parts. First, what we do to create physiological digital twin. And we'll cover two parts of that. First, the platform that we have developed in order to study physiological twins, and how we are looking into mobilizing the community to solve this important, relevant problem. The second is to look how we can really leverage now this platform to shine light on the basic principle that allows human dexterity and agility to emerge. In particular, we show two studies. One to look at the generalization, how we can generalize through movements, and the other one, how we can speed up learning if we start using human embodiment on terms of features that are characterizing the human learning at the motor level. Let's start with the physiological digital twin. We have known for decades we have had decades of understanding of the peripheral actuation. Biomechanics has done an immense and amazing job at characterizing the mechanics of the peripheral of our nervous system. And above all, one of the instruments that has been more instrumental to this understanding is OpenSim, which is an open source project from Stanford University. This has been a collection of models and tools to develop and characterize musculoskeletal actuation. Nevertheless, OpenSim, being a biomechanic focus only platform, has the limitation that it really doesn't look into scalability, trying to address very complex and full body muscle model, and also contacts with the world. And we know that we don't live completely isolated from the world. Our embodiment is acting in world. We touch the world, we interact with the world, we interact even with our own body to understand it and to learn from it. So our first step, trying to evolve from this understanding of the biomechanics, was to convert the biomechanics models in OpenSim into a platform that allows us to leverage more feature. That is, MyoChallenge is a physics simulator that has started originally for robotics, and now is maintained by DeepMind, and has the ability to be very, very performant. Has been very, very popular in machine learning because of this performance and stability and accuracy. Now, this project has been led by Alexi Ikala and Wai Wang, who have produced this converter that's called MyoConverted that allows us to preserve geometries, momentar, and muscle forces. And now, once we move into MyoChallenge as a physics simulator, we gain speed. MyoChallenge is very, very fast and highly scalable, and mostly we obtain contact dynamics, so that now these models have the ability to interact with the world, interact with the environment that they are put into. So we started this project releasing a very simple elbow model, just 6 muscle, and with a proof of concept, we add an exoskeleton to this model. And this is really to show that actually this platform is a robotic platform. So the synergies between the robotics and the musculoskeletal is there by definition is really a platform that allows to simulate combination of control, both at the robotics and the musculoskeletal level. One of the most complex models that we started, and this was really a challenge for the community to do something unique, was to release a full hand model with 39 muscle. This was the first hand model that was able to manage and articulate very complex objects with all the degrees of freedom of the musculoskeletal system continuously and to learn new features about the hand. And then more recently, we released legs and a full arm with all the complexity of the shoulder as well. Now, those models are very efficient, and you can even just use them in the browser. And I really invite you all to try this because it gives you a different perspective of what it means to control a body at the muscle level. So this web page, you will be able to move the hands or any other of the model that is presented there through muscle activation. And we realize how complex it is to move to achieve a given posture and to maintain that posture. Really will change your perspective what it means to control something of the dynamics of the musculoskeletal system. But those models by themselves do not mean much. This model have a sense as our peripheral system if we are embedded in the world. We do not just have a body, we use our body. We use our body to do something for a goal, for an objective. And this was the motivation behind MyoSuite. We really want to create a collection of environment and tasks of the same nature of humans, tasks and goals, but they need to be actuated through the same actuation that humans have, that is the muscle control, the musculoskeletal system. This is done in MyoChallenge for scalability and accuracy, and it's done through a very simple API, a Gym API, OpenAI Gym API. This allows us that in just a few lines of code, you have complete control and access to those musculoskeletal model tasks. This is an open source project from the community for the community. It's not attached to a single lab or single person, and you can freely leverage it from the GitHub, and are also very inclusive. Everybody can contribute and can join the team. So just to highlight what are the major features, and you can see on the bottom some of the major contributors to date of MyoSuite. So the two major features of MyoSuite are that it's very, very fast, highly scalable, and actually very computing efficient. You can run this on your laptop. You don't need a big infrastructure or a complex infrastructure. You can run on any operating system or even on cloud. It's very, very lightweight, very, very flexible, but it's super fast. It's very fast, and original benchmarks show us that it can be up to 4,000 times faster than state-of-the-art methods. But most importantly, enables contact-rich interactions. This really allows us to interact with the physical world. And by combination of scalability and contact-rich interaction, we can really start looking at physiological behavior to understand and tame what is the complexity of the human actuation, human motor system while behaving in the real world. Now we just released a few tasks, and it's already hundreds of different types of manipulation. You can imagine this can be an infinite number of objectives and tasks that humans can do. And we just started with a few of them, that both in terms of manipulation, locomotion, or in-hand dexterity. But what I want to stress is that this platform has been built by design to tame the complexity of the musculoskeletal actuation. So from inception, we had fatigue model that more recently we have enhanced through the work of Florian. Apologize, I forgot to add his picture, this slide. So he has contributed this three-stage fatigue model that allows us to show what are the effects of both fatigue and recovery. So in your world, you continuously are exposed to fatigue, but also you recover from fatigue. And that's an important dynamic system to consider once you are actuating the world, that you will not be able to perform always at the maximum strength because your muscle will fatigue. So those are features now that are included in MyoSuite, and you can take advantage of in your simulations. Given the complexity of the simulation apparatus, really there are a lot of practical applications where MyoSuite can be used. Can be used for rehabilitation. So you can test what might be the different process that might be taking in terms of stress to your joint, your muscle, while you are interacting with therapeutics. For example, this is an example of a bowling ball experiment where the hand was tasked to rotate two balls against each other. And you can see in orange, the lighting up is the activation of the muscle that are necessary to perform these specific movements. Or you can use that for testing what happens when you have a surgical implant. For example, you have a tendon rupture or you have deficit of some ligaments in your body. How your motor behavior change affected by that. Also, you have a really good platform to start to test new exoskeletal control, as you have a complete robotic actuation system that can be embedded together with the musculoskeletal to shared autonomy. Now, when we started MyoSuite, we came from different backgrounds. The original contributors to MyoSuite came from neuroscience, robotics, prosthetics, graphics. We really had all different bias in coming in, and we realized that actually all were interested in one thing only, and it was the shared point between us. We were interested in human motion. So MyoSuite really came together to be an intersection of different fields. We were interested in motion analysis, taking understanding of how humans move, both in terms of dynamics and kinematics. We are interested from the machine learning perspective to understand how a complex actuation system made of hundreds of muscle with non-linearity and third-order dynamics were able to be controlled in order to perform skilled tasks. Coming from graphics and computer vision, how the expression of movements then becomes something that is accurate and appealing visually for making some realistic movements. And also importantly, the biomechanics. How this understanding really allows us to get a better way to understand how our peripheral actuation takes place in the world. Now, one thing that we realized earlier on is that we came from different communities. We found a common point in MyoSuite, but still those communities have made a lot of progress in isolation. Every community has defined their own standards for defining a body, what a body is, how it is articulated. Some fields cares about inertia, others does not. Some care about physics in terms of contact, some others not. And everybody has defined their own standards. And this is really something that we cannot allow to make progress because everybody is still interested in those different fields to human movements. So one big step that we took this year is to define a universal model that we call myoskeleton. So the myoskeleton wants to be a universal parametric skeletal model that is really agnostic of the field. It can be used in different fields, has all the features that can be literally adopted and leveraged independent on the field that you are. It's an open source model like all the other models that we have developed, and you can use from the original repository or is already integrated in MyoSuite if you want to already embed it in task and take advantage directly into MyoSuite. Now, this is really unique in a way that allows us to be really agnostic of the field, but still be able to connect to all those fields together. We have now a skeleton that is fully articulated, has all the inertial information for any physics understand that we want, has all the contact delays to enhance the understanding of interaction with the world, with the environment. And mostly is a hardware accelerated. This is a very highly scalable and fully differentiable model that can be used in any pipeline. Also, natively, MyoJoco and this model are also integrated in Unity. So you can even extend this model to games to more flexibility in terms of definition of the environments and tasks that you want to provide. Also, we integrate this model with MyoSuite. So all the tasks that we are doing now can take the expressiveness of the full body model. Even if the actuation might be localized at different muscle, the model now is fully activated at all levels of the body. So we can start looking at the body as a complexity of a multifaceted actuation. It's not just legs, it's not just an arm, it's not just one part of the body. Now we have a full body to refer for any type of actuation. We create an interface with SMPL that is the most adopted standard for computer vision. These are parametric scheme models that can be used to characterize and define computer vision models. And we were going to release soon an interface that allows SMPL to be directly interfaced with a myoskeleton and to be used both into MyoJoco or outside MyoJoco, so that we can have all the flexibility of the myoskeleton, MyoSuite, but into a computer vision pipeline. And last but most importantly, this is a fully actuated system that allows us to support any type of musculoskeletal details. So we have now a common ground to project and understand the full body dynamics. This also enables another opportunity. All those fields have produced a massive data set and really leverage from scaling data collection. But they have a work in isolation. So each one has defined what are the features that are important and what are the type of data that are collected. And missing a common ground to bring all those fields together limited the possibility to understand human motion in a much more comprehensive way. So the myoskeleton represents now a common platform where we can map all these data sets in a common way. We call this a Myo dataset, just for summarizing all the complexity of the data that we can provide. And it's an open source project led by Hawking. So it's an open source project. If you want to contribute, if you have data and you want to help in, please reach out and we'll be happy to receive any contribution to make this the largest and the best database of human motion, agnostic of the field that the data comes from. Now, while we were building MyoSuite, of course, we use MyoSuite. We just don't build all the tools. We use that for our own research. And we came across a very simple observation when we start training our models to solve tasks. That when we give task a fixed objective, so we give always the same initial condition, always one goal, and very little variability, we can use brute force reinforcement learning or brute force machine learning to solve those tasks in pretty good way. Those are regional results. They hold true still, but more complex environment results that we have nowadays. But as soon as we introduce variability, that is both in the randomization, the initial state, on the randomization of the behavior that we want to achieve, we observe a huge reduction in performance. So really, the current machine learning method, when we start working on this baseline, we're not able to tame the complexity of actuation, the complexity of the task that every human does normally. We don't just do the same task from the same stationary condition. Always we have new condition noise everywhere in our system to change to have variability that affects the variability of what we do and how we interact with the world. So this represents a big opportunity, not only to try this task, but really to engage the best mind around to try to tame these problems. So what we did was to partner with the NeurIPS, that is one of the Neuro Information Processing System conference, that is one of the largest conference in machine learning, and we proposed a MyoChallenge. So this was an evolution. In the previous years, we saw that there was interest in biomechanics, so the community was open to this complexity, so really want to propose something unique that scales up all the possible complexity of human actuation. And 2 years ago, we proposed two different tasks. We proposed in-hand manipulation of two types. One was the rotation of a die. So the task was to rotate a die to achieve a specific phase of it, or the other was to coordinate the rotation of two objects, a body and ball task, where the task was to rotate those against each other. And the objective was to perform this task through the use of the musculoskeletal actuation of the Myo hand, so 39 muscle control, controlling 23 joints. And we were evaluating the solution across two dimensions. One was success. You had to be able to achieve the objective with a given error, but also the effort. How much effort in terms of muscle activation was put to achieve that in order to minimize fatigue and to minimize the overall muscle contraction needed to achieve that state of control. So this was one of the most well-attended conferences in NeurIPS. We had more than 40 teams participating all over the world, from more than 10 countries. We had a lot of submissions across two phases. We had 340 submissions, and really MyoSuite was being used massively during this time of this challenge with more than 2,500 downloads. Now, in this challenge, it was very successful in terms of solution adopted and strategy adopted. But we observed something, again, very, very interesting. So you can see the solution of the winning teams on the right, both of the die rotation task and the body and ball task. And on the left, you can see the statistics of the two phases. Now, in the phase one, we had the deterministic task, something that had always the same condition without randomization. And you can see that both tasks for the die rotation and body and ball, people were pretty good. In body and ball, they even achieved perfect score in the solution. But as soon as we introduced the randomization of initial condition of physical properties of the object, we had a huge drop in performance, with the rotation only achieving 13% of success and the body and ball only achieving 55%. This really speaks that even in this competition, we're not able to achieve a perfect accuracy in solving complex tasks when non-stationary conditions are presented. So this really was motivation to continue and challenge with more complex tasks. So last year, we had another MyoChallenge, and I will let Cheryl to present it.
Thank you, Vittorio, for the introduction. So I'm Cheryl Wang. I am a PhD student from Yale University and also part of the MyoSuite team. So very happy to be here at Johns Hopkins University to give you a little bit more information on MyoChallenge and from past year, and also more information on how you could join and participate this year. So for MyoChallenge last year, in addition to our first introduction to MyoChallenge 2022, we introduced two separate tracks. One of them is manipulation, and the second one is locomotion, which uses the upper limb and lower limb respectively. So the manipulation track asks the participants to grab an object using the Myo arm and place it into a receptacle or a bin that is located within the range of the hand. And for the locomotion team, we actually designed the competition to mimic that of a chase tag competition, which the musculoskeletal agent will have to either chase or evade on a 10 times 10 meters terrain, just like that of an actual human competition. Next slide, please. Thank you. So a little bit overview of how we did last year in comparison to our first release of MyoChallenge. We actually have a 50% increase in the numbers of teams that participated. We have about almost 60 teams, and this spans across 15 different countries. And over two phases of the competition, which is just a little bit more than 2 months, we have over 500 submissions. And during this time span, you also see that the download of MyoSuite tripled. So this actually shows that our competition is actively engaging the community into looking at biomechanics system and solving this musculoskeletal system together using machine learning techniques. Next slide, please. So also a little bit of review of the scores that we did last year. We also have two phases. Phase one is deterministic task, which doesn't introduce any variation. On task two, we introduce a lot of randomization and non-stationary. So for phase one, we see that MyoSuite participants actually perform quite well. over the two different tracks. One of them achieves 100% and the other one achieves 84%. However, when we're introducing phase 2 variation, and this includes, for example, in manipulation track, we're introducing randomization in object masses, frictions, locations, as well as the starting and ending receptacles locations. When we introduce those, and when we introduce different and even terrains that will randomly appear in the arena, we actually see a huge drop in the performances, just like what we see in the first year of MyoChallenge. So this potentially implies that there are better policies and generalization out there for all of you guys to explore and develop in the upcoming challenges. Next slide, please. Okay, so building upon all of the challenges that we have introduced in NeurIPS in the past year, starting from the Myo hand to the Myo arm and the lower limb, this year we'll actually want to introduce physiologically dexterity and agility in enhanced human. So this means that we're actually wanting to introduce bionic limbs that integrates with the musculoskeletal simulation and agent that we have currently in the MyoSuite model. So the reason that we're introducing this combination is that we not only want this competition to be a breakthrough in the machine learning or reinforcement learning community, but we actually want this to benefit people outside of the field and reach the communities such as biomechanics and healthcare. And we want this to be potentially helping all of the patients and develop control methods to prosthetics and exoskeletons in the future. So let me introduce the competition of MyoChallenge this year, 2024, the manipulation track. So this year we'll be introducing the bionic Myo arm, which is a combination of our past Myo arm and also the modular prosthetic limb, which is actually developed by the very own university we're giving this talk in, Johns Hopkins. So the Myo arm has 27 degrees of freedom, and you can have 63 muscle actuators that you can control with your reinforcement learning agent. While the MPL have 27 degrees of freedom and is actually torque actuated. So your policy will actually have to generalize over those two different controls in order to achieve the task that we'll be introducing. So a little more information on the task this year. So this year we actually will require the participant to co-manipulate between those two different types of limbs. So an object will actually appear on the pillar on the right, and you will be grabbing it with the Myo arm. And you will need to perform a successful pass over from the Myo arm to the MPL limb on the right and place it successfully onto the pillar on the right. So the object that you will need to maneuver can be any daily object such as a pen, drill, toolbox, etc. But we have settled on a Jello box, which you can see easily in your kitchen and can be easily grabbed with just one single hand into the palm. So the participants, all of the participants for this challenge will be ranked on 3 different criteria. The first is the score, which is the number of successful trials which you have placed the objects onto the right pillar. The second criteria is the time, which is amount of time you took to complete the trial. And the less amount of time you took, the higher your rank. And the third criteria is the effort, also known as the muscle activation, so which means that the less muscle that you activated, the better the policy you will rank in the competition. So we have attached a link here for the MyoChallenge 2024, which links to our website, which has more information on tutorials, code, more information on seeking help, forums, etc. And we encourage you to seek it out. So I'll also hand over to Qinghuan, I think, who will be introducing the locomotion track of this competition.
Right, thank you, Cheryl. So my name is Qinghuan. I'm also part of the MyoSuite team. I'm from Northeastern University. I'm a postdoc working with Songman over here. Okay, so for this year, the locomotion track features the open source leg with 2 degrees of freedom in the knee and ankle. And we have a simplified, MPT model of a myo leg with 20 degrees of freedom and 54 muscles. So in this case, as you can see, the right leg has been have undergone this transfemoral amputation with muscles that cross the knee being removed from it. Okay, so what we have is like at least for this model, is a little bit special that you don't get to interact directly with the open source stick, but instead you only access it, or you have to learn the movements and dynamics of it through the contact forces from the socket you have on your residual limb. And yeah, we think this is like so for this task, it is you're supposed to traverse over different terrain. So if you actually follow our maybe announcements, you would have noticed that you're supposed to traverse over rough ground, some slopes, and also stairs. So given that the distance is something we are interested in as a metric, so you actually rank on how far you can get the model to travel. And on the other hand, we also include a physiological objective where we look into like a minimal pain and muscle activation. So pain in this case is defined by reducing the amount of joint overextension torque you are generating on the residual limbs and also on your other good limb. And so because of that, we do understand that it might be difficult for maybe biomechanists and non-RL people to try to tackle this challenge in this complete way. So we do have a way where we include the first 20 meters of the track would be actually considered for this physiological objective. So if you would like to participate, then yeah, then this is what you should be looking out for. And I guess probably at this point I could maybe hand it back to Vittorio.
Sure. Thanks, Cheryl and Chungwang. So, okay. So the MyoChallenge has started already. We released the task, the initial task in July, and there was time, there is time to try them, to test them, to start setting up pipelines for training. We will open the scoring stage next week. So rather than to have two phases like last year, this year we'll have just one single phase so that you can focus and more optimize your time for submission just in a shorter period of time. And this will be where you start getting ranked and all the awards will be also decided on. So please get ready. Next week, we open it up. The competition will last until the end of October. Then we'll communicate the results in December, and we'll have a workshop on December 14th, where both the winner's solution will be presented, but also we'll have experts in the field joining us to have a very heterogeneous and integrative discussion like we always have for those workshops that we call MySymposium. They are workshops that we invite experts in different fields really to cover a breadth of interest and approaches in musculoskeletal or human movements. We started also a new initiatives this year that are the advocates teams. So we have a team of international people that volunteers to join to help us to reach deeper and broader in the geographies and communities so that we can have a more representation and also understand geography specific limitation in participating in those challenges. We have a big coverage already, but this is an open team that is really welcoming new members. So if you are interested in joining, please reach out. We'll be happy to welcome you to the team. Now, if we look at the world before we started with MyoSuite, we look at peripheral actuation in a very constrained way. It was slow, was mostly looking at postural activation, was really not embedding the world. MyoSuite really opened up the possibility to have those musculoskeletal actuation in the world, actuating and interacting with the physical environment. But this is not enough. As humans, we don't just do one task. Over and over, just we learn to perform only one single task. We are continuously exposed to a huge variety of tasks. And that's why already in the MyoSuite 2.0, we start looking into generalization in terms of task structure. So we start releasing environments that the solution needs a lot of diversity and generalization. And this is really to better connect how our human intelligence is encoded. We don't really build one solution. We build representation that we update over time. And just want to give an example of that on what happens in locomotion when we move from toddler to adults. on the top part of this figure, these are color maps of activation of the spinal cord produced from muscle, a reprojection of muscle activation on the spinal cord. It's a little bit technically complex. Let me just simplify. If you see the color transition, those are basically activation over time of different muscle groups. And what is important on this feature is that when you move towards different stage of your growth, you don't change the combination of the actuation that you have. You build on the previous experience. So even basic pattern of activation when you are a toddler, they are maintained while you grow your body, you gain more experience so that you learn without forgetting, you learn new tasks more quickly, and you enlarge and you stabilize your learning. And this brings how we can use MyoSuite really to shine light of this learning, how we can use that really to understand the levels of human dexterity and agility. That will be the second part. We'll try to be fast on this part to take some time for questions. So if we look at diversity of behavior, we can look at how trajectories of objects are in space. You can immediately glimpsing on this trajectory of this object, understand what is the intention behind the movement. If a cup is used for drinking, if you use it for pouring water, so to move that around. But actually to understand the goal, you don't even need the object, you just need the trajectory. So that the same goal can be achieved with different objects according to the trajectory that of the movement that is performed. Now, how do we get information about the object? Well, actually, we don't need really information about the object because the object itself is not informative enough of the goal. What do we care is about how we grab an object. So this concept of affordance is that each object can be grabbed in a different way according to the goal and the purpose that it has is a well-established concept in psychology and neuroscience. And basically, the concept is what you see in this picture. You can have the same object that, depending on how it's grasped, indicates different goals. For example, a goal to move it around, to pour water or prepare liquid from that, or just wash it or handle it for different purposes. But what we know also about affordances is something that you don't even need the hand in contact with the object. The information about the affordances, the hand shaped in a conformed way to manipulate an object, is something that is not happening before the hand-object contact, so that you pre-shape your hand to a given posture. And this work from Castillo really shows in these graphs how the aperture of the hand is established much before the hand-object contact. This is the point that you see the transition on the right. Now, if we don't need to get in contact with the object, we can get the posture of the hand before this contact. And you can see here a collection of hand pre-shaped for a given object and given goal in this picture. This is a concept popularized as a pre-shape of the hand towards the goal of the object. And we did an experiment where we used the Myo hand to manipulate those complex objects, but we added translation rotation at the level of the shoulder. The time we didn't have yet the Myo arm with the complexity of the shoulder, but we want to give the ability of spatial movement. Now, if we have the trajectory of the movement and we have a pre-shape of the object, then we can look into learning behaviors. And this work done in collaboration with Sudeep Dasari and Vikash Kumar, published last year at SEML. So the basic idea of this project is that we have an actuation space that is our muscle, and we can observe only information about the joints and the position of the object. So there is no tactile information on this, no visual information. And even in this constraint, we are able, only through the pre-shaped and the trajectory of the object, to learn dexterous manipulation. This is a sample of different manipulation, and you can see how the hand is able to perform to manipulate the object to achieve these complex behaviors. Now, when we look at the variety of different behaviors, we look at a sample of 57 different behaviors, we notice that only minority, or only half of those were able to be solved through a brute force single task policy. And this is because what happens that in the musculoskeletal actuation, you have a lot of local minima. You have a lot of issue in getting stuck in local solution. They can be degenerate, or you're not able to explore properly the space. Now, we are in actuation space that is muscle-based. So what we can look is to muscle coordination across different tasks. And when we look at the muscle coordination expressing as muscle synergies, so that muscle that are working together in order to achieve a task, what we learn from the different solutions, this is a sample of 14 solutions, is that each solution, the muscles were contracted, were activated in a completely different way. So basically, each solution was independent from each other. So there was no sharing of information between those different solutions. Now, these tasks are tasks in isolation. We don't, again, I said before, we don't learn tasks in isolation. We learn to perform multiple tasks in our life. So what we can use, though, is that we have learned something from those solutions. We can use that as an expert, and then we distill from those experts one solution. Just leveraging the experts. This is actually not really physiological. We don't learn just one thing in our life, then we learn another thing, and then we merge those information. We are continuously exposed to different tasks at the same time. So what we do is mostly to be a multitask agent. So what we do is to get exposure continuously to different objects, to different goals, maybe learn that at different times, but still we get continuous exposure. And we call this approach MyoDex. Now, when we look in the solution space, on the left, you have the goal of rotating this clock, alarm clock. The expert in the center is, of course, able to solve this task, and the student learning from the expert acquires all the distillation of the information from the expert, so it's able to produce almost identical motion. But actually, MyoDex is able to perform this action as well. And you can notice the details of the hand are slightly different than the expert, but still able to perform the task properly. Here is another task, is a stamping of a stamp. Expert and student, again, almost identical solution. Expert able, again, to solve the problem, but with a slightly different solution. Now, if we have a solution that is independent from the object, just need a pre-shape, and is independent on the trajectory, we can just give a new object to grab. So we can give, in a zero-shot environment, a new object, this duck, and the task just to lift it. Now you can see that the MyoDex in a zero-shot setting is able to perform, or at least initiate the action, but lose control of this object. Again, it doesn't have any information about the shape. It can just know the position of the object. So if we give a few shot learning, we can then refine the movement, and we have a perfect reconstruction. And this holds true for many other tasks. We visually can do a huge set of tasks, and all will be able to be solved through this pre-learning, this learning that we have initiated. Now, looking at a large set of tasks, so we take 14 to train the initial phase. We can look at the 57, so the 43 complementary. So only 16 of those were able to be solved by experts. Even a minority by the student gets even more constrained than expert in generalizing into solutions. But MyoDex is able to solve 3 more times solutions, almost all of them. And actually, we have some ablation experiments to show why we are not perfect in this task and how we can get perfect to this task. Now, it's not only able to solve more tasks, it's also able to solve them faster, because it just needs a few shots to learn most of the new tasks without much effort. So in general, it's 4 times faster to achieve the same learning behavior than other methods. But the most important, we can look in the master space. So in the master space, students that inherit the same constraint and learning from the expert are not able to share solutions with experts. But MyoDex, that by construction was done to share solution, to learn something that generalizes across tasks, share also the same muscle representation between different tasks. So basically, you are reusing the same muscle groups and the same muscle contraction in a modular way to achieve the task. And this has been a question about how the organizational movement allows that to happen, that has been really puzzling scientists for the last few decades, how muscle synergies really help to understand perform motor behaviors. Very quickly, this is just on extraction of muscle synergies, but can we use really then to learn new tasks? So in another study, what we did is to learn from a simple set of movements in hand manipulation, extract synergies, and then use those for learning new, more complex tasks. This is a work led by Cameron Berg in collaboration with Kash Kumar, published last year RSS conference. Now, the objective of the task is to rotate in a hand a large set of objects, 100 objects. And what we do is that we do a pre-training with just 10 objects. Just 8 objects. Then we extract synergies, and then we use synergies on the top to learn to manipulate more objects, or we can use a curriculum learning. So we just learn a simple set of objects, and then we take that to learn a more complex set of objects without synergies. Or end-to-end, we try to learn the 100 object altogether. So if we look at the performance very quickly, only the SAR method, that is synergistic action representation, the method that use synergies, over time is able to, in the same time budget, is able to learn to manipulate this large variety of objects, but both the curriculum learning or end-to-end learning fail. The metrics of success on the left are color-coded in different methods. On the right, you can see the manipulation of the end-to-end baseline and the SAR approach in rotating objects. As shown before, because of the approach is really extensible to different objects, we can enlarge now with even more complex objects that were completely out of the distribution of the original set, with everyday objects with very different complex structure. And this can go even beyond manipulation. You can use the same approach in locomotion, learning a very simple couple of steps, and then generalize the movements to complex movements like climbing stairs, diagonal work, working on rough surfaces, or even up and down hill. Let me wrap it up. So through MyoSuite, we really have put together a platform that is able now to understand and that is able to allow us to study the human motor actuation through musculoskeletal actuation, and to learn what are the fundamental building blocks of manipulation that will allow us then to understand motor intelligence. And the two results that I show you, MyDex and SAR, they show you how is it possible to leverage this understanding for generalization, both in domain and out of domain, and how to use muscle synergy to build new motor learning faster and better than previous methods. I just want to say this is not just my work. This is the work of many people that have contributed in different ways to this project and these results. Just a few are presented in this slide, but there are